This is the summary of frequency responses of all the filters. So this is the frequency response of low pass filter. So what do you see here? So here we have the frequency in the x-axis. You know, omega is equal to 2 pi f. And here we have the gain. So mostly we represent analog filters gain in terms of dB. This is a standard one. We just have to follow this. Okay, so now this low pass filter is passing all the low frequencies. Maybe I change the pen color. So it passes all the low frequencies. When it starts to become a high frequency, maybe the same example we can take 1, 2, this is 25 and this is 50 kilohertz, and then this is 75 kilohertz, and this is 100 kilohertz. I give you the numerical example because you can easily remember. So this 25, it passes this and up to this 25 kilohertz, the filter is passing, so it's a high, the signal, the output is high. And then after 25, there is no more output. Output becomes 0. So it means it stops these high frequency signals and it passes only these low frequency signals. That is called low pass filter. Similarly, the same graph we can draw for high pass filter. In the high pass filter, same here, we have frequencies in the x-axis and then gain in the y-axis. So here it stops all the low frequencies. It passes only the high frequencies at the output. So this is the frequency response of high pass filter. This, remember, we are talking about ideal frequency response. We are not talking about actual frequency response. It's always different. That's why in the beginning of the lecture, I told you the difference between ideal characteristics and practical characteristics of operational amplifier. So it's also part of the assignment. So in the ideal characteristics, we always assume this is the infinity, this is 0, input impedance is 0, output impedance is infinity, bandwidth is infinity, and so on. That is for the mathematical calculations and derivations. But in practical, when you really talk about the filter design, the filter response, frequency response is not like this sharp. You see here, it's coming 0 and then exactly sharply turning up. So it's sharply rising up and then it's giving from the 75 to 100 at the output. So since this is ideal frequency response, this is okay. But in practically, it's not like that. I will show you that also, the difference. So now this is the high pass filter. It passes only the high frequency signals. And the band pass filter. So as I told you in the beginning, in the first part when we start the lecture, so the band pass filter is only passing certain band of frequencies. So in our example, we had seen the number 26, I think, up to 74 kilohertz, right? So it does not pass from 1 to 25 kilohertz. So the output is 0. But from 26, it sharply rises up and then it passes the signal. The output is high. And then after 74 kilohertz, it falls down sharply and then it blocks the rest of the frequencies. So it blocks here and here. It passes only specific band, selective band. So it's called a band pass filter. And band stop filter is the opposite operation. So we do not want this band. So the filter is just only passing these low frequencies 1 to 25. And then it falls down immediately and then it stops this frequency band between this range. And then again, when it reaches 75, then it's rising very sharply up and then the output is high. And then we get, for example, here in this example, 100 kilohertz. So this is the definition. Low pass means only allow low frequency signals below cutoff frequency. So we have to always find the cutoff frequency. So cutoff frequency is, we had already seen cutoff frequency for a differentiator and integrator. Remember what is the formula for that? 1/1 divided by 2 pi RC. So the same actually, because if you design the filter by using resistors and capacitors, then you are going to use the same formula in this filter design also to calculate the cutoff frequency. So for the low pass filter, you have to calculate this cutoff frequency. So you remember, you please note down this point. Below cutoff frequency, it passes the signal. So if I calculate the cutoff frequency as 25 kilohertz, so it means below whatever the frequency of this 25, then the filter will pass these frequencies and it will block the rest of the frequencies. So below the cutoff frequency, this filter is passing. So in the high pass filter, it's the opposite. So it only allow high frequency signals above the cutoff frequency. So I calculate the cutoff frequency, for example, as a 75 kilohertz for this high pass filter. It means it will block whatever the frequency is less than this cutoff frequency, and it will pass only the signal frequencies which is above this cutoff frequency. So that is what I mentioned here, above cutoff frequency. Because in each filter, we must calculate the cutoff frequency. Without cutoff frequency, we cannot really calculate the things clearly. What signals are passing, what signals are stopped or attenuated. And band pass filter also the same. Here we have, you can see here the definition, only allows certain frequency range from a specific frequency number until another specific frequency. So for example, here specific frequency means 26 kilohertz. From 26 kilohertz up to 74 kilohertz, it passes. So it means here we have to calculate two cutoff frequencies for band pass filter. So it will only pass, for example, this is the FC1. FC1 and this is FC2. So it passes only between FC1 and FC2. Okay, so only between FC1 and FC2, this band pass filter is passing at the output. And band stop filter, here also you can see we need two cutoff frequencies that we will calculate for this band stop filter design. So it allows all the frequencies except certain band. This is except this band, it passes all the frequencies at the output. So it rejects particular band or frequency range. So then in this case, we have also FC1 and FC2. So except between FC1 and FC2, so it excludes the frequencies between FC1 and FC2 and passes the rest of the frequencies. So here it includes the frequency range between FC1 and FC2, only passes this one and block the rest. So as I said, like this is the ideal frequency response. Now we will see the practical frequency response. So practical frequency response means what? This is what happening in the real-time filter. So I designed the low pass filter. So I want only from 1 to 25 kilohertz. So it's not sharply falling down at the 25. So when the frequency is getting close to 25, already the curve, the output start to fall down. You see here, it's going linearly down. And then maybe I will reach complete zero at maybe 30 kilohertz or whatever the number it is. So here the curve is going linearly down. So, but practically we want the curve should be very sharp like this. But remember, it's almost impossible to design ideal filter. We cannot really achieve ideal frequency response like this. So practical filter design, the frequency response will be like this. So, but what we can do, we can improve this linear region. So instead of falling down like this, I can make the fall down as sharp as possible. So instead of falling down here, maybe I can make it more sharp, like maybe I can make it to fall down here. So instead of starting 0 from 30, maybe I can make it 26, 27. So that is what we can do practically. So as you make this curve as sharp as possible, so then yeah, that is why you have to go to the higher order filters. Okay, so here in this low pass filter, it passes the low frequency, but the ideal filter frequency response is like this. The high pass filter is also the same. So for example, the first few kilohertz, of course, you want to allow the frequency only from 75 kilohertz to 100 kilohertz at the output. But when the frequency is around maybe 65, 70, already the curve start to rise up. It means you are starting to get the output, some minimum output at the output terminal, and then it will rise up linearly. This is called a linear raising, and then it will reach the maximum value at the output. And the band pass filter is also the same. So here you can see here, so it will be like this. And the band stop filter is also the same. So it's not sharply falling down. So it's just linearly raising, linearly falling. So we have to design the filter to make this curve as sharp as possible to rise or to fall. Okay, so practical filters, it will not fall very sharply like ideal filters. Yes, that's correct. There is a curve that will fall or rise linearly with respect to time and your filter design. So how it's falling down, it's really based on your filter design. So that is why you have to do if you are designing only a first order filter, the linear region will be very long, but that's not what we want. So that's why we have to move to the second order filter, third order filter, fourth order filter. Simply we can call that as a higher order filter design. So for more higher order filter design, the falling or rising edge will be more sharper. So maybe, for example, here I have this is with a just a normal single order filter design. So I make this is a first order filter design. I make into the second order filter design. Then the curve may fall down here. Then I make the third order filter design. Then the curve may fall down here. And then the fourth order may be here. And then the fifth order almost here. So I cannot go more than that. There may be some limitations. Because how do you make this one? You are also, it's also depending upon the R and C values when you design the filters. So there is always a limitation in practical filter design. So we will see them now. So just to try to remember, when we go to higher order filter, higher and higher order filter, then you will get more and more sharp falling or rising at the output. So the order here refers to the order of the polynomial that are used to design the filter or define the filter. You may use MATLAB and practice on some examples. If you are really a MATLAB guys, then you can download MATLAB. It's free here in the university for academic purpose. You can also design these filters and then you can see the frequency response. You can also use Simulink. But of course, this is not part of the course requirement. But if you are more interested to analyze these frequency responses, you can do this MATLAB and Simulink or Simulink. So in Simulink means like it's like a model based simulations. So you will get the component. For example, you will get the operational amplifier and you will get the resistor and you will get the capacitor. So, and then you will design the filter and you will just bring the components and then you will connect with the wires and then you will make the entire circuit and then you will do the simulation and you will see the digital oscilloscope at the output. Everything is just on the laptop or on the computer. So you are not going to use the real-time oscilloscope. So if you are interested, you can download this and use this one. There are so many tutorials also available in the MATLAB website. Okay, but this is, as I said, this is not compulsory. This is optional. It's up to you.